Snow is a common effect in video games because who doesn't love ice levels? And what better time to make a snow shader than March, when the cold weather's on its way out? In this tutorial, I'm going to create a snow effect in which snow piles up slowly over time, and we'll be able to control the direction that snow attaches to a mesh. I'll give this shader a lot more properties than I usually do so that it's highly customizable. This example project will be available on GitHub in the description if you want to poke around without copying the shader yourselves. There's also a link to my Patreon and Ko-fi accounts in case you want to fuel my coffee addiction and help me get higher quality content out faster. And if you like this video, the subscribe button is sat right there below this video, looking a bit lonely. Go give it some attention. I'm using Unity 2020.2 and URP for this tutorial, and we're going to start off by right-clicking in the project window and selecting Create, Shader, Universal Render Pipeline, Lit Shader Graph, because I want to use Unity's lighting system automatically. I'm using this beautiful old log cabin model by Nikolai Fedorov on the Unity Asset Store, and a ground texture from cc0textures.com. I've already created the shader, so I'm just going to step through it part by part. The first step is to add a whole bunch of properties for the parts of the shader that are nothing to do with snow. That includes a base colour and a base texture, which we will combine to form the albedo colour of the unsnowed material. Is unsnowed even a word? Then we'll need a normal texture and a smoothness texture for some extra lighting detail on objects, plus a normal strength float in case we want stronger normal mapping. To control the UV mapping on these textures, we will add tiling and offset properties, both of which are vector 2s, with default values 1, 1 and 0, 0 respectively. I've prefixed the word base on each of these so we don't mix them up with the snow properties we'll add later, and apart from that, there's nothing really special about any of these, so we won't go into any more detail. The only property so far that doesn't interact at all with the snow is the normal texture, so I'll go ahead and plug the base normal texture into a sample texture 2D node with its mode set to normal, while using a tiling and offset node to make sure the UV mapping is correct. That gets passed into a normal strength node with the base normal strength property plugged into the strength pin. All this gets output to the normal field on the master stack. And now we can deal with the snow features one by one. The most important characteristic of the snow is that we can control its direction. The snow will usually only land on the top layer of objects, so we will provide a vector 3 property called snow direction to describe where the snow will render. On the graph, we can take the dot product between the snow direction and the normal vector of the mesh to give us a measure of how closely the surface matches the snow direction, although I make sure I normalise the snow direction vector first to make sure its length is 1. The dot product might act weirdly if this isn't the case. Then I saturate the output to bound it between 0 and 1. Next, we will add the ability for snow to form layers over time and build up in clumps. We will need 3 more properties. Snow amount is a float between 0 and 1, which determines how fully the snow has layered up. Snow blend distance is another float which controls the size of the blending region between the base texture and the snow layer, and build up noise size is a float which we will use to control the size of the noise clouds used for the snow bunching up. The basic approach here is to take a noise cloud and use the snow amount as a step threshold to determine the shape of the snow clumps. We'll start by adding 2 simple noise nodes and plugging build up noise size into the scale pin on the first one. For the second, we will multiply build up noise size by some amount. I use phi, the golden ratio, or approximately 1.62. Then I take the mean average of both by sticking their outputs into a lerp node and setting the t value to 0.5. This gets passed into a smooth step node, which is where we apply the threshold to the noise. In the edge 1 pin, I use 1 minus snow amount. In the edge 2 pin, I take that and I add snow blend distance. The smooth step node output is 0 whenever the input is less than edge 1, 1 whenever the input is greater than edge 2, and blends between 0 and 1 whenever the input is between edge 1 and edge 2. The result for this shader is a noise cloud with a fairly hard transition between black and white if the snow blend distance is low, but with enough of a transition region that it doesn't look unnatural. We then multiply by the dot product we did before and saturate to bound between 0 and 1. We're starting to get much of the core calculations out of the way. We're almost ready to deal with the base texture, but first I want to add texture variation to the snow. We will add snow color property for fairly obvious reasons, plus 2 floats called snow color noise size and snow color noise strength. These property names are a bit of a mouthful, but I hope they're descriptive enough. We'll take the dot product from before, then multiply by snow color. Then we can add noise to this. Add yet another simple noise node and give it our thanks for carrying this entire shader. Then use snow color noise size for its scale. We will remap the values output from this node. The in-min-max values, that means the minimum and maximum expected input values, are 0 and 1. We'll keep the maximum output at 1, but snow color noise strength will become the minimum output. Finally, multiply the remap with the snow color multiply node we just made. The next step requires no extra properties. Take the base texture and use a sample texture 2D node and a tiling and offset node like usual, but keep the default sampling type. Multiply that by base color, and that leaves us with what should be the base albedo color. We're going to blend between this and the snow color, so pass this into the first input on a lerp node, and the noisy snow color we just created into the second. For the t parameter, we need a measure of how snowy this pixel is supposed to be, which is exactly what we calculated before using the smooth step node. Take the output of that group and plug it in here. Then we can output directly into the base color on the master stack. This leaves just the smoothness map. Yet again, use a sample texture 2D node and a tiling and offset node with the base smoothness texture and connect that to a lerp node. This time we don't really have any fancy calculations for the smoothness of the snowy areas. I've just set it to 0. The t value is the smooth step snow buildup value, just like it was for the base color. Then output that straight into the smoothness on the master stack and we're done with the shader. Ideally, I'd have loved to do something more interesting with the shader, such as physically thickening the snow as it builds up instead of just using texturing tricks, but unfortunately we can't yet use geometry shaders in ShaderGraph, and I think that would have been the easiest way to pull off something like that. I've written a short script which animates the snow amount over time and added a snow particle effect to tie the scene and the shader effect together. If you implemented this effect in a game, you might want to slow down the build-up speed, but this is just an example. As always, this video is powered by my Patreon supporters. By joining, you can get your name in these credits, as well as a custom role in my Discord channel. The next big shader video will be the winner of February's Patreon exclusive poll, a look at The Legend of Zelda Breath of the Wild's grass in the form of a geometry shader, which means we'll be using shader code instead of ShaderGraph. The grass in that game looks gorgeous and I'm really looking forward to making this effect. Until next time, have fun making shaders.